that I'm teaching today is not for the exam. So I'm staying alone, I understand. Okay, what I want to do today is basically see how we treat field theory which has interactions between particles and the fields. So we have seen how to solve field theories that has phi square in it, some derivatives of phi, but these are basically non-interacting particles. We have seen explicitly for phonons and said that it's similar for photons. And what happens if we have interactions between particles? Then we can solve it exactly, and we are doing some kind of perturbation theory. And the most ubiquitous and popular perturbation theory is basically Feynman diagrams. So hopefully at the end of this lecture, you'll have some vague notion what these Feynman diagrams stand for, what all those squiggles try to express. The lecture actually has two parts. The first part, I guess it will be the first 3/4 of an hour, perhaps a bit less, perhaps a bit more, will be pure mathematics, or even more explicit, Gaussian integrals. The second part will be actually a demonstration why these Gaussian integrals help us to solve the case where we have interactions, and we'll concentrate on one specific case, the phi to the fourth term in the Lagrange. Okay, so we'll start from something that I don't know if nowadays it's taught in high school, but certainly in the first year. Hope I don't surprise them. Someone can remind us how do we solve it actually?
You move to polar coordinates.
Move to a two-dimensional representation. Yeah. We do the integral square, polar coordinates, and that's the action while you have here square root of pi. Okay. Of course, this is correct only if it's larger than 0, smaller than 0, it just diverges. Something very similar okay, we turn it into x minus something square, change variables, and that's what we get. And the final, almost final, trivial case. If we have Gaussian integral over z, where z is just a complex variable composed out of a real and imaginary part. So just replace z and z conjugate by the appropriate x plus iy and x minus iy, and we get this result. And the equivalent to this case not that I'm going to do in this lecture anything about these complex variables, just if we have a field theory where we have complex fields and not scalar ones, so we need these things. Okay, as I said, this more or less at the beginning of your undergraduate studies shouldn't surprise you. Let's move to something a bit more complicated. Maybe you have seen it in statistical mechanics. So this is an integral over a vector, meaning something that has parameters v1, v2, v3 till the n. So this is simply okay. And here I have just the multiplication of the vector with a matrix.
Like the Dirac exponent.
It appears in a lot of places in physics. Okay, and the answer is the determinant to minus half of the matrix. A is a matrix, of course. Okay, I want to prove it. It's really easy. One caveat. A is real and symmetric. If A is real and symmetric, there exists some diagonalization, some transformation where I can write it down with values only on the diagonal. So let's assume I know it. So A is equal where this is diagonal. And of course, the O transformation is unitarian. So I can take what's written here and do the transformation V equals O, matrix O times V. By definition, okay. Because D is diagonal. Okay, here we have just a set of Gaussian integrals of the type built here. Okay, so that's why this is correct. Okay, so we had the equivalent of the integral on top here with a matrix. Now we'll see the equivalent of the second integral here. And we can go using the same game and obtain which is equivalent to the b squared over 2a period. Just because we composed it from each one of those d's and perform the integration. Okay. And perhaps the most important integral that we'll need here. So we are multiplying the integral by a specific v somewhere in the vector and two specific values n and n. Instead of doing dx to e minus something x squared, we are doing dx x1. So okay, what did I do here? Basically, derivative according to m and n, the only place that it depends on j is here. So it will move down Vm, Vm. And when I'm taking g to 0, I'm losing this part. And back to this integral. To remind you, everywhere here, if I want to do dx times x, e to the power minus ax squared over 2, I can do a derivative according to b here, remove it down, and go and get the result. There actually a simple change of variables, putting u equal x is easier, but in principle I could have done this game. So okay, this guy, I know exactly how to do it. So here. Okay. All this part doesn't depend on j. Just a moment. Yeah.
מה זה אומר לגזור לפי איבר בווקטור? אם האיבר הזה חוזר על עצמו במקום אחר בווקטור, אז...
Okay, let's see exactly here. There's all, from all this complicated thing, a place where Jn and Jn appear is only in one point. Jn, Anm, Jn, right?
לא, אבל לפני זה, מה זה אומר איבר JM? יכול להיות שבאיבר הזה יהיה רשום בדיוק כמו באיבר JM פחות אחד. מה זה אומר לגזור לפי איבר בווקטור?
I'm thinking of J as a vector, meaning n components, and each component is a variable that I integrate over. Okay, it's a variable. So I can integrate upon, I can differentiate, right? That's all. Let's see something.
Why is it -1?
For the same look on these integrals, A always appears
Okay.
below. Oh, sorry. But it's the same reason. A appears below. You were right in the previous writing, but pay attention. They are all very similar. If you just want to check if you are doing something horribly wrong, just look on the first two integrals. That gives you a good intuition to what is happening for the more complicated ones. That's why I started with these. Guys, and if we would have gone and done something connected to complex fields, we would see something very similar with Hermitian matrices. Well, but today we're only handling the simple scalar ones. Okay, just definition. This is a definition. If I write something in between these points, I mean that multiply these points, everything that appears within the bracket, by this whole integral. Not in a moment, in a few minutes we'll see why is this good. But let's write as an example. Similar to this, but with 4 different V's, different or equivalent. same logic as we did for 2. And I'll write already the result. I have to have something where all 4 appear, and this could be in 3 different combinations. Just how many different options you have to contract 2 out of 4 cases, so on and so forth. Okay, so who cares? Okay, if there are mathematicians here, they'll stone me for not being careful. No one's picking up any rocks, so be okay, or perhaps I didn't say yet anything. But in general, every time that I have a vector and a matrix, I can replace them with due caution sometimes, with a function and a function of 2 variables. Why? Because I'm taking the finite vector, I'm thinking of infinite number of, this is actually a function. So everything that I wrote here for vi, I could think of it for vx, where x is a continuous variable instead of I a discrete one. And anywhere that I have a ij, thinking of a function of 2 with x and x prime. Anyone who did anything connected with computers has many times performed the opposite. They put his function on a grid, put his operator on a grid. That is exactly. So what we have here, basically this is a function, and this is, and I'm jumping and not filling in the gaps, this is an operator. If you want, that's the deep root why Heisenberg matrix formulation of quantum mechanics was equivalent to Schrödinger's wave function. Because for this guy's vectors are the same as functions, and operators are the same as matrices. Okay. Instead of doing an integral over v1, v2, v3, v4 that we did before, I'm doing a functional integration over vx. What does it mean? Taking all the possible configurations of v over the system, which is equivalent. Which is exactly the integral written here. Instead of summations over I and j, I have integration over x and x prime. Instead vi and vj. If I had here complex, so this would have been the complex conjugate. So the result of this integral So the structure is exactly the same structure that we have written before. We have one small thing that should cause you some indigestion. This goes to infinity. Because here I don't have n anymore, n goes to infinity. So we'll do the distancing and not look at it. That's why I said that mathematicians will have problems here. We won't have problems because we'll never look on this standing alone. We'll always divide it by something that has the same divergence, and as a good physicist believes that that's okay, mathematicians will say you have to check carefully and understand what you have done here because you are dividing two divergent terms. But the only thing that is left open here what is the inverse function of A? For a matrix, we know very well what is the inverse of A, which appears here. At least in principle, we even know to perform it. Here, the requirement is the same thing as a requirement for finite matrices, meaning that makes sense, similar to the definition. And just by continuation of the logics that but you remember those brackets say basically do the integration here with Vx and Vx prime here. There's the same logic. This one, and the last thing I need here forms a part of your mathematics. Okay, write it down. Okay, I'm going back to the simple integrals.
What is the determinant of A if A is a function?
Was the same playing fast and loose, I don't care. The determinant will also be killed by the same procedures that I kill the pi. Okay, therefore I'm writing her similar, not one. Okay, so I know it's a lot of mathematics basically in a short time. So the last thing is back to simple integrals. We did until now everything with bilinear forms. X squared basically, everywhere. X could have been a vector, but, and I said we want to do here something that it has a field to the fourth. Let's see. Okay, G equals 0, we're good, we know how to perform it. Okay, so I want to write it down as a sum over some kind of some kind of an expansion. And here I assume an expansion in small g. Why do I expand in small g? Because I don't know to do it for any g. What does it mean for field theory? This type of expansion, or the logic of this type of expansion, will work for g, small g's, weak interactions, won't work for strong interactions.
למה ברביעית זה אינטראקשן?
Because, okay, very simple. Square, you solve, and solve that you have actually 3 particles as a solution. Meaning all you have to say, I have 7 particles in the first mode, 24 in the second, and so on and so forth. Did you care if there are 7 or 8 to define in the first mode in order to define the second mode? No, they're non-interactive. So the simplest way to put in interactions is to look at higher terms beyond 5 squared. Okay, what will you put there? 5 to the 3 won't work. Why? Simple. You're taking a 5 to the power of 3. You'll have 1 creation and 2 annihilation, or vice versa. No good. Well, very good. That doesn't have any influence on your result, right? Unless you can couple your system somewhere to an external path that gives that you can put in or remove particles. But in general, no. So the simplest form of something that is not trivial would be 5 to the 4th. Okay, that's why you call it interaction. Okay, I'm just expanding e to the power minus gx to the 4th, and powers of x to the 4th. Okay? This guy I know to solve. So, no one actually assures me that this is something that you can actually sum up and not diverge. Experience tells us that you usually in these types of expansions you have some n max that, and if you sum up to this point you get the best solution, the closest to the truth. And basically Feynman diagrams is basically this. We, instead of looking at x squared or phi squared, we expand it and sum up till some point. Usually the point where in the beginning one or two terms is what you have patience to do, and you hope that it gives you the right results. The 50s and 60s, there were a few very diligent physicists that went on to the fourth and fifth term in the expansion. Nowadays, people like in CERN are going and feeding their computers and getting to whatever expansions they are getting nowadays. But that's that. That's what you can do. Works very well. QED works till 10 or 11 decimal digits. QCD, where the interaction is not weak, you can't do anything in this form, and we have a huge problem. But there are going to other tricks like lattice QCD, going and putting it from the beginning on the computer in some kind of lattice and pulling out something. Although at the end of the day, when you're doing QCDs, weak and strong, the strong interactions, nothing is as good as the QED expansions. And then when you're going to string theory, basically nothing can be expanded and no other good ideas, and we're stuck there. No predictions come up because you can write the equation, you can't do anything. Okay, so till here mathematics. Now we'll use these results. Basically, all these integrations you will see again, or you have already have seen in advanced statistical mechanics. Someone has taken already the course?
I'm now taking it.
You're not?
Advanced statistics.
Advanced.
You're taking that now. This semester. No, this.
No, we haven't seen it.
Wait.
Okay, I'll refrain from
Mean
commenting.
זה דומה קצת למה שעשינו ב...
Is it mean field? זה קשור למין field integral?
No, it's even before that. All the Z functions that appear there basically have very similar structure to these.
You even got to the point of something like what you did here. Something different, similar.
Okay, so basically, field theory and statistical mechanics, people are used to talk of them as equivalent up to an imaginary part in time. Basically, time becomes temperature in statistical mechanics. Again, it's a very loose association, but a lot of methods that come from here or come from here can appear in both. Okay. So this is the action of a phi-4 field theory. Why d to the d? Just to think cleverly, and you can basically treat your any dimension. This term we have seen. This term we called it n. We have seen, solved it completely. This is new. Integration over the action. Go back a bit to the beginning of the course. Well, it's advisable at this point that you'll go a bit over the beginning of the course. And this is an interesting quantity. What did we do here? Basically, we took the definition of the integrals that we have shown before and divided it here to get rid of these 2 pi's to the power of n and the determinant of a. Doesn't appear here. Okay, and well, I'll go back to statistical mechanics. E to the minus beta E divided by Z. Exactly the same idea. And I can do this integral also without interactions, and then I call it 0. The only difference is I take the action with no interaction, meaning I lose this term. And actually the name of the game would be to calculate this property with interaction by somehow expressing it only as terms with no interaction. Okay, at the moment it's not clear how we'll do. Okay, we'll start with a non-interacting green function. Does green function has it any meaning for you? Okay. What does it mean here? This is basically a different way to approach questions regarding a quantum system. Okay, what did we do till now? We basically came and said, look guys, I want to find the eigenfunction and the eigenvalues of the system. Right, that's what we're doing throughout your undergraduate studies and at least for almost all of the course, the advanced. Green's function comes to answer a different type of question. The same as the solution of a differential equation using green function or solving it explicitly. Can someone sum up what is the basic idea in green function when I'm solving a differential equation with green function? It's not the mathematics, it's the idea behind it. You need mathematics to express it. Basically, it's a very simple, green functions answer very simple questions, which are very similar to what we are really doing in real life or in experiment. And the question is the following. You kick the system at point x1, which means at position and time. And what is the response at point x2 after some time? So in the language of quantum mechanics, I add a particle to the system at point x1. Remember, x1 stands for time and position. And ask what is the probability of, or probability amplitude of finding a particle at point x2. Point again, position and some specific time. And basically, what does it mean? It means the same integral over action with x1 and x2 in the integral. General philosophy, what it means? Usually when you're solving a differential equation, you need to be supplied with boundary conditions, right? This tells you what are the boundary conditions. I start here, and I want to end up here. What is the probabilities that will happen? And since almost all experiments in particle physics are at the end of the day scattering experiments, you throw in particles that you have accelerated to huge energies or momentums in your accelerator, and see where they appear in the detector. So basically, all these experiments is you start at some point, you end up at some other point. So we are not trying to solve the eigenvalues of this interacting problem. We're not trying to come up with the energies of this interacting system. We're trying to answer this, what is a green function, which for practical use is really what you need. I start with some disturbance in the system at point x1, disturbance adding a particle, see if I see this particle or see a disturbance at point x2. Okay. That's exactly that. Start with x1, x2, and g0 of this. Okay, what do we know about the zero condition? The condition with no interaction. Actually, we know that we could have solved it exactly by moving to the p space, performing Fourier transform. We did it. So instead of playing the game in x, we'll play the game in p. That would be much easier. And we have an additional benefit to it, which is basically, what is the big difference between x and p? At least for finite boundary conditions or for cyclic boundary conditions, p is discrete, and we always find discrete calculations easier. So I'm writing was diagonal in P. So I'm using the eigenfunctions Vp. What I want to calculate meaning that's exactly a scattering problem. I start the particle with momentum p. What will I see what is the probability amplitude that I'll see it at p prime? Let's start doing the intervals. This part, the lower part, Here I'm not even, because it's discrete. Don't worry to write it to pi and the determinant, everything is fine. It's diagonal, so that's the determinant. Okay? Okay, so I just written it down. Okay, why this is exactly a to the minus 1 pp prime? Because it's diagonal, I have this delta function. I can't just choose any pp and p prime because all the non-diagonal terms here are 0. Okay, so here happily I go and insert what I got here and here in the definition of the green function. And I end up with so basically, what does it tell us? It tells us basically that, here for you the answer, why am I sure it's non-interacting? If I start something with P, will always continue with the same momentum. I can't change momentum. What does it mean I can't change momentum? I have no interaction. Okay, what does this 1 over p squared plus r squared mean? Here it would be actually easier to understand if we'll transfer it to x to the real space. So since P is conserved, it only depends on x2 minus x1. It has nothing to do with the specific points that you started. Makes sense. Remember, this is the probability amplitude. Square is the probability. If R is equal to 0, you basically have diffusion. Otherwise, you have a probability that goes down with the distance. Okay, great. What happens when instead of this nice and cute case, we have interactions? Okay, so well, I've erased it already. We see that we expanded with the 4 terms. So let's start from the first, and that's the only thing I'll do here. So basically we'll have integrals so to remind you, the interacting part is okay. Basically, I take the terms in the expansion till n max. Don't worry, here I'll take n max equal 1. Okay, so how does So I want to calculate phi x prime. Same that I did here, the only difference, no 0. Okay, so this is the first term in n, and actually this is zero term, which is just the non-interacting. This is the first, and I have additional terms that at the moment, not in this course, we won't go into it.
Why is it 0, the second term?
What?
Why the second term is 0? Index.
This term is not this?
Yes.
It's not zero.
No, why did you write down 0 in the index?
Okay. Because what do I do? Go back to the original integral, the simple integral with g to x to the fourth. What did we say? Expand g to the... But all the terms x to the fourth, x to the 8, x to the 12, and so on are not going into the exponent, right? So from the point of view of doing the integral over the exponent, which is exactly this bracket, you see, it's 0. So I complicated the calculation by having an infinite number of terms, but I simplified it that each term I'm doing the procedure with only the non-interacting part. Interactions added this term. And here you can actually see very clearly, okay, what I forgot here is minus g over 1. Next one will be g squared. The number of terms here can grow. But if g is small, the whole contribution will go down. That's the expansion here. Okay, so let's see what we are doing here. So basically I'm writing it explicitly. That's why I invented the notation not to write down. But what did we see? We saw that anything with 2 or 4 or 6 or whatever, you're just building all the contractions, all the pairs that you can pull out. Right, so this became a question of what pairs do I pair here and how many of those do I have. So and the only thing I've forgotten here is dd to the right. No other way to combine them to pairs. Pay attention, I still didn't count how many different combinations do I have here. But what is the result? I can't see the result even before I count the number here. This guy is basically G0 x minus x prime. Right? Starts at y and end at y. Okay. Okay.
Is this an approximation or something?
This is the first term in the approximation, but in this term I didn't do anything.
So you write down.
I have still to integrate on.
So why did you close the bracket after two?
Because that was exactly the results that we got, if you remember, in the 4 case. Exactly that. No approximation here. The approximation is, of course, there are additional terms. Now, and here is the genius of Feynman. Came and said, well, to keep track of this whole calculation is complicated. Let's help ourselves by using a graphical description of what's happening here, and that will help us basically to keep track of our calculation. Okay, let's be explicit. Let's give a beginning point x and an end point x prime. This is actually what we want to calculate. And put in a vertex of G. Combine all possible permutations of connecting these lines, and you'll get all the terms that appear here. So what do I mean? Let's do this thing. I directly connect this one to this one. And connect these twos. So now I'm looking what I have here. G0 goes from x to x prime. And here twice it returns to itself. Exactly what's written here. It's no magic, it's just a way to keep track of what is happening here. Okay. How many different combinations we have here? Combining x and x prime, only one. Let's choose color. Here I have 3 different ways of combining these 4 legs. The first one I can combine either to this, or this, or this. Right, all of them are kosher. And the next one I have no other options because I'm left with 2 and those 2 have to be connected. So I have 3, so I have 1 times 3, so this guy is 3. Okay, what else? So this is this 2. What else can I do? Can take my x, connect it to one of these, take my x prime and connect it to one of these. Let me just, for the neatness, connect it up and connect this guy with this. So this is gx minus y. This is g0 x prime minus y, and this is g0. Exactly what I have here. How many different ways could I do it? Well, x, I had 4 points that I could connect. X prime, I have only 3 left, so I have 3. And the remaining pair has to connect one to the other. I have no choice anymore, meaning I have a contribution of 12 such terms. Well, again, I could do the combinatorics directly here, but this is much easier to keep track of what's happening here. It's just looking what diagrams, what class of diagrams you can, and counting how many different ways you can connect. So, you're now experts in Feynman diagrams. Of course, I can have much. Here I have only one. When I have 5, 4, I have still only one type of particle. If I have more than one type of particle, let's say vertexes where a particle is created and another particle emerges out of it. So I have vertexes of 3. Let's say an electron which comes in with some momentum p, comes out momentum p prime, and emits a photon. Now this photon can be swallowed by someone who came with P prime and came out with that, and this photon transferred such momentum. We've seen it, these types. This is Coulomb interaction. Okay, again. So G0 here to the point of emission. G0 forms a point of emission. G0 of a photon from here to here. That is the first contribution. Or, without explaining anything, this is a virtual particle. It comes in with P, goes out with the same P, nothing is transferred, but you have some renormalization of what's happening here. So whoever goes to advanced condensed matter will acquaint himself with such diagram. So this is the whole secret. Depends on the form of the interaction, but you break down your green functions, your processes, into non-interacting processes with intermediate something happening, a vertex, an interaction. And each time that you have such an interaction, a power of G, a power of the interaction, comes into your game. Now, well, basically, to get the end results, I have to perform, after I calculate the appropriate G's, I have to perform the integration over Y here. Physically Y over Y, because this interaction can happen anywhere in the system. It's not constrained. I know where it begins, I know where it ends, but I don't know where this this interaction occurs on the way. It can occur anywhere. And that's that. And that is the basic way that we treat interactions. As a perturbation over a sum over possible interaction events. And anything in between happens with the non-interacting case. So a particle goes for a time, is non-interacting, that's the G0, has an interaction, something happens at some point, and then continues again as a free particle. And as long as interaction is weak, that is the philosophy that how we treat interactions. Okay, so we'll stop here. It's the end of the course. As I said, this part is not in the exam. The only thing, we actually missed two things that come into this course sometimes. One of them is electromagnetic field quantization, but anyone who does quantum optics will run into it in that course. And path integrals, and anyone who does an advanced condensed matter will see it there. I would have preferred to give you some taste of it, but that was as the time was available. Okay, thank you.
Thank you.
Thank you.